So now we're going to talk about the atmospheres of the terrestrial planets. And this little picture here is just like a joke to talk about the fact that one of the things we're most interested in when we think about the atmospheres of the terrestrial planets is the fact that there might have been water on Mars at some point. So if we want to talk about the atmospheres on the planets, we need to know what we mean by that word. Basically, an atmosphere is a layer of gases that surround a world. The air is made up of different gases that they may be individual atoms or they might be molecules. The common atmospheric gases that we're going to talk about within our solar system are nitrogen, oxygen, water vapor, carbon dioxide, hydrogen, helium, methane, and ammonia. The main constituents of the Earth's atmosphere are what? You might be surprised when you see this. We're mainly nitrogen and oxygen. I'm sure you were going to guess oxygen, but you might have also wanted to combine it with carbon dioxide because of the talk about the greenhouse effect. But even though the greenhouse effect is caused by carbon dioxide in our atmosphere, it's actually a very small constituent in our atmosphere. It's a very small percentage of our atmosphere is carbon dioxide. So the atmospheric pressure is something that we are going to talk about because it helps us sort of compare the atmospheres of the different planets. The atmospheric pressure is basically the pressure that you feel on you due to basically the weight of the molecules that lie above you. And so it might, to us, you know, you're so used to it, we're acclimated to it, so we don't even really notice it. But you can sort of think about how the atmosphere, how it might feel differently if you think about what happens when you dive into a pool and when you go into the deep end. You feel like sort of the pressure in your ears and you might feel uncomfortable, and that's because as you go down deeper into the water, the weight of the water exerts a higher pressure on you. And so I just talk about that because when we think about atmospheric pressure, because we're so acclimated to the atmospheric pressure that we feel here on Earth, we might not even really think about it as being very important. But basically, it's also caused by the atoms and molecules are constantly moving and running into each other, and as they run into each other, they're creating this pressure. So here is sort of an illustration. If you have a balloon, of course it's full of air molecules, but the balloon is being held up by the pressure of the gas molecules inside of that balloon. And those gas molecules are moving around, and as they hit the edges of the balloon, they sort of keep the balloon up. At the same time, think about the fact that there's air molecules outside of the balloon that are also hitting the edges of it. And when the balloon is staying sort of static and constant, it's because the pressure of the interior molecules is exactly equal to the pressure of the molecules outside of the balloon. We know that if we blow into the balloon, we add more air into the balloon and the balloon will expand. What we're really doing is we're adding molecules, and that's actually going to increase the pressure. We also know that if we heat the balloon, the balloon will expand, and that's because now the molecules will move faster. If we cooled the balloon, if we put it in the fridge or in the freezer, it would immediately start to sort of deflate because of the smaller temperature would cause the molecules to not move as much. So we're seeing right here that the two things that are sort of important in determining the pressure are the temperature of the gas and the number of molecules. As we go higher into the atmosphere, the density of the atmosphere decreases and the pressure will also decrease. We can think about what happens to you when you go to high altitudes. You have to sort of adjust your body to that, and that's because the atmospheric pressure is different and your body isn't used to that. If Mars and Earth each had the same amount of air for each square inch of surface as the Earth, how would the atmospheric pressure on Mars compare to that on Earth? You might want to think about that. You might have thought it would be the same, but it's actually going to be lower because of the pressure is also going to be caused by the weight of the gas, and because of the lower gravitational field of Mars, that's actually going to have a smaller effect. So why do we even care about atmospheres? Well, one of the things that an atmosphere does for us is it helps keeps the planet warm, and it does so through the greenhouse effect. We're so used to these days seeing or hearing about the greenhouse effect in a negative way that it might be hard for us to understand that it could actually has been a positive thing for us already on Earth. Because if it weren't for the greenhouse effect that the Earth has always experienced due to its atmosphere, we would all be freezing and probably life would have never even developed. The atmosphere also helps to absorb light, which is absorbing the energy from the sun, and helps to warm us. And it also acts as a protector, because it will scatter some light and prevent it from penetrating the atmosphere. It does create pressure, and of course everything on Earth has been acclimated to the atmospheric pressure that we do feel. And it also can play a role in the weather. Finally, there's an interaction with the solar wind particles in the magnetic fields, which create the aurora, or what you might also know as the northern lights. Here we're going to take a look at this table. Now, there's a lot of information on here, but some of the things that we want to focus on, first of all, let's think about what are the atmospheres made of, and let's see how they're similar and different by looking at this column. So we notice that Mercury and the Moon are similar in their makeup, in that the atmospheres consist mainly of helium and sodium. Mercury has some oxygen, the Moon has some argon. So that's how they're similar to each other. Let's just go across with those two objects because they're very similar in that respect. Notice the pressure. Now the pressure is measured in bars. 1 bar is the pressure we feel at sea level on Earth. Notice that on both Mercury and the Moon, it's 10 to the minus 14. It's just really, really small. So what that's really telling us is that the atmospheric pressure on those two objects is basically negligible, which means that they have really almost no atmosphere. As they do have no atmosphere, one of the other things that we're going to notice is wild temperature swings. Look at that for the Moon and Mercury. Of course, because Mercury is closest to the Sun, it can get extremely hot, but you might be surprised how cold it gets. That would be when you would be on the planet facing away from the Sun. And part of this is because Mercury rotates so slowly, it will be in the dark for a very long time, allowing it to become very cold. But it's also due to the fact that there's no atmosphere to hold in the heat. And likewise on the Moon we see these wild temperature swings. Now let's take a look at some other planets and see how they might be similar. If we look at the makeup of Venus and Mars, we notice that the sort of how their atmosphere is made up, or the gases it's made up of, are very similar, which is interesting. But then there's this huge difference in atmospheric pressure. And what that tells us is that Venus has an incredibly thick atmosphere. The pressure you feel on Venus would be comparable to what you might feel about a mile underwater. So it's really just horrible, horribly thick. While the pressure on Mars is very, very thin. Now, of course, it's not as thin as the Moon, but it is still very thin. And then we can sort of see the effect that it has on temperature. Notice Venus with its very thick temperature has very high temperatures. It's actually hotter on Venus than it is on Mercury, even though Mercury is much closer to the Sun. And that's because of its thick atmosphere can hold in the temperature. And then when we look at Mars, the temperature is actually pretty cold. That's partly due to the fact that it's pretty far away from the Sun, and also that the thin atmosphere doesn't allow it to hold in much heat. Finally, we look at Earth, which has more of a unique atmosphere. It has a lot of nitrogen, oxygen, and a little bit of argon. and we see that the temperature on average is pretty hospitable. So why is an atmosphere good for a planet? Well, some of the things that it does, as we've already said, is it helps keep a planet warm. The planet's warmer than it is with the atmosphere than it would be without, so that's definitely good for it. And that's actually caused by what we call the greenhouse effect. And so if we want to sort of see how the greenhouse effect has been positive for our planet, let's look at how warm a planet would be without an atmosphere. And in order to think about that, the things that are important is how far is the planet from the sun and how much sunlight does the surface absorb. Some planets will reflect light very effectively, which means that they don't actually absorb it very efficiently. And so how reflective a planet is will determine how much of the energy from the sun it actually will absorb and use to heat it up. Of course, as we get further from the sun, the delivery of that energy is more inefficient because the energy is being spread out over an increasingly larger area. So this table is pretty similar to the one that we looked at previously, just in that there's a lot of information in it. And what it's really trying to show you here is for the different planets, what their temperature would be if without any sort of greenhouse effect and what it actually is. So what you might be very interested to find is that Venus and the Earth would be, actually, we would expect them to be quite cold without their atmospheres. In fact, they'd be well below freezing. And that's why I said that, up until, modern times, the greenhouse effect on Earth has actually been to our advantage. It's actually helped us keep warm enough so that Earth is a place that's hospitable to life. Of course, now it's become a little bit of a different type of problem. Notice that Venus has such an extreme greenhouse effect that the temperature is so very hot. Mars has a very subtle greenhouse effect because it does have a very thin atmosphere, so it is slightly warmer than it would be without its atmosphere. The way that the greenhouse effect works is basically this. Light comes in from the sun, and that light is energy. And that light is absorbed by the surface of the planet, and then it's released. It's either reflected, and some can be lost out into space, or it can be absorbed and then released as infrared radiation. And basically what happens in the greenhouse effect is there are certain types of gas molecules that are very efficient at absorbing infrared radiation and then re-releasing it. But because they absorb it and re-release it, they actually kind of slow the process of the infrared radiation, which is basically heat. They slow the process of that being lost into space by sort of re-releasing it in random directions, and so the heat stays in the atmosphere much longer because of the greenhouse gases. Common greenhouse gases, of course, carbon dioxide, but others that you might not know as well would be water vapor and methane gas. So it's the existence of these gas molecules in a planet's atmosphere which are responsible for the greenhouse effect. We're going to stop right here talking about the atmospheres, and we'll continue with the next movie.